Good morning, everyone. Today we're going to be examining the usage of Gradle in the Ratpack open source project. I was going to take questions throughout because I was a little worried it would be complicated jumping between topics, but given the shorter time slot, I think we're going to wait to the end and see if we have any time left. I'm David Carr, and I'm a systems architect with CommerceHub. I've been working there in Java and Groovy for many years now, and I have a special interest in build projects, having organized many of our build refactors and switches between Ant and Ivy and Gradle most recently. I'm also a contributor to the Ratpack project. I wrote the majority of the config system for that. So what is Ratpack exactly? In terms of its basic function, it pretty much is a web framework. You write web applications in it. It's async based, whatever. Unlike some other frameworks, however, it operates solely as a set of Java libraries that you compile and run against. You don't install Ratpack as an operating system package or run Ratpack by itself. You just build an app using it like you would any other library. Due to this, the Ratpack project is a great example of a Gradle build for the project. It's non-trivial, it's got lots of different modules and enough Gradle logic that it's meaningful to see how it interacts, how it's organized. It also ships with a few Gradle plugins, which are useful as examples of Gradle plugin development practices. So, let's start with an example of a minimal Ratpack project using a Gradle build. In this case, using the RatpackGroovyPlugin. Here's the build Gradle file. It is pretty small for a minimalistic Hello World app. First, we declare, hey, we actually want to use the RatpackPlugin. In this case, I'm using the new plugin syntax, not the old one, but they were both supported, whatever. We declare what repository we want to resolve artifacts from. I like JCenter, Maven Central works too. And though it's not strictly necessary, we need some SLF for J binding for the Ratpack logging. Otherwise, you get all sorts of errors and warnings, just warnings, that, oh, you don't have anywhere for your SLF for J logging to go. You're not going to see any logging. That annoys the heck out of me. So if we run it now, we would get a no ratpack.groovy found message. That's not very fun. So let's create one. First, we import the main entry point for a Groovy Ratpack script, and then we use it to define a single get handler, render some hello world. When we run it, it compiles the app and starts up a Ratpack application, fully functional. Send a request to it, it'll give you hello world back. Great. But that's not that useful for a busy app developer. We need to make changes. We need to have quick response times on being able to test those changes. So we have integration with Gradle's continuous build feature, which was just mentioned in the keynote. When you run it with -- continuous, it not just builds the application, it also starts it up, and it's tied into the continuous build lifecycle so that it is informed of the, hey, a new build is ready, and gracefully shuts down the server, starts up a new one with the new code. It detects this automatically whenever you change any of the source files that were part of your project, and as Hans said, queues up future builds so that if you're making multiple changes while a build is running, it starts another one immediately after the current one finishes. It leads to a really quick turnaround time on testing changes. So that's all well and good. How do we accomplish that in the plugins? There's also several things that would normally be present in a web app build that weren't here at all. For example, there weren't any dependency declarations for Ratpack itself, or Groovy, or any of the other libraries that are needed to make Ratpack run. There wasn't any specification of how to run the application, where to find the entry point. All of that is configured by the plugin for us, so that the developer doesn't need to. It's done automatically. It's a general good practice when writing Gradle plugins to separate them into two types of plugins, capability-based and convention-based. In Ratpack, most of it is convention, but we do have a little bit of capability, which is our RatpackExtension. So our base plugin is a capability-based plugin, which does one thing and one thing only. It installs the extension. We'll talk a bit about what the extension does a bit later. For Java projects, you apply the Ratpack plugin. There's a separate RatpackGroovyPlugin that we saw used in the example. The Ratpack plugin builds upon the base and adds in the conventions that are commonly used in Ratpack projects. Here, we declare what our minimum acceptable version of Gradle is, check to see what version is currently in use, and fail if the version isn't high enough. Because we've got a number of internal Gradle features that are being used by the plugins, and it's just not going to work if you're using one that's too early. Better to give accurate feedback early than get lots of support requests saying, hey, this thing doesn't work over here. I don't know why. It's just not a good experience. Then we apply the application plugin, which provides the basics for the run task as well as being able to start Java processes easily. And the Ratpack base plugin, which we talked about, installs the extension. The Ratpack extension we then look up because we're going to use it later on in the plugin. We get the source sets from the project, and we register a new source dir for the main source set's resources. Our entry point class, that source Ratpack, ratpack.groovy, if we hadn't registered that as a resource, continuous build wouldn't know that, hey, that's something we're actually supposed to look up, and it would just ignore it. After that, we add some dependencies to the project. This is where we automatically have access to Ratpack Core. We're also registering the Ratpack test utilities as a test compilation dependency. Note that we're not actually specifying what group, what artifact ID, what version here. We're asking the extension to do that for us. So let's go to the extension and see what that looks like. The extension keeps track of the path to the Ratpack directory, which we saw is used to register it as a resource. It also keeps hold of the project's dependency handler, which allows it to create dependency objects as needed. We have knowledge in the extension of what the group for Ratpack artifacts is, as well as what version of Ratpack is currently being used in that plugin. So we publish new versions of the plugin in lockstep with versions for all of the other Ratpack artifacts. And when you use a Ratpack plugin 1.1.0, it automatically pulls in Ratpack Core 1.1.0, Ratpack Test 1.1.0, Ratpack Groovy, Juice, whatever. It also has convenience methods for getting the related artifacts to Ratpack Core. So in the previous slide, we'd seen that it has a core and a test, which are certain well-known artifacts that are commonly used. There's also a Groovy and a Groovy test. And if there's any of the other modules in the Ratpack distribution that you want to pull in, you can directly use it yourself. You can say, give me ratpack.dependency metrics or RX or whatever module it is that you want. And it will give you the version that version of Ratpack shipped with. After setting up those initial dependencies, we tweak the run task that was provided by the application plugin. Here, all we're doing is setting a system property so that it knows that when you run Gradle run, it should run it in development mode as opposed to normal mode, and can tweak some of the application behaviors to deal with more intelligent caching for a developer experience. And in previous versions, runtime config reloading, blah, 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 some of those things got shifted out of things that Ratpack itself cares about and into the continuous build feature now that that's available. There's also some logic in the Ratpack plugin specifically about integrating with the continuous build lifecycle. But since that's an incubating feature that's changed a bit between several Gradle versions and uses a bunch of internal classes, I'm not going to cover that in detail right now. The RatpackGroovyPlugin builds on top of the Ratpack plugin, applies the Groovy plugin, and defines a main class for the project. In a Java project, if you don't specify a main class explicitly in your build file, it'll just not start because it doesn't know what class should be started. With a Groovy plugin, that Groovy Ratpack main automatically knows, hey, I should look for a ratpack.groovy, and if so, run it. Alternatively, if you're using the Groovy plugin, but you don't like that default startup model, you can just specify a main class name to override it, just like you can with any other project that uses the application plugin. After that, we add some further dependencies. We add a dependency on the Groovy library, as well as the Groovy test library for utilities useful in testing Groovy Ratpack projects. That's pretty much the extent of the implementation of the plugins. So let's talk a little bit about our testing. Ratpack's plugin testing is built around Spock, which is a testing tool, and the Gradle test kit. The Gradle test kit is a capability provided by Gradle to do functional testing, primarily of Gradle plugins, but it isn't tied to plugin testing in any way. You can use it to easily automate runs of Gradle for whatever purpose, with arbitrary versions, arbitrary environment variables, options, targets, and capture the output thereof. Here's an example of a simple spec that uses the functionality we have in our test framework. All of the logic for actually interacting with Gradle test kit is abstracted out into a parent spec, the FunctionalSpec. And it also provides utility methods to run tasks, assert that they should either succeed or fail, capture the output, create build files.
So is that FunctionalSpec something you created, or is that something?
It's something we created, and we'll see it in a couple slides. But It's not really tied to Ratpack in any way. If you want to steal it, feel free. It's all open source. Here's an example that actually builds and starts a Ratpack app. The main difference between this test and the previous one is that after we start it, we need to figure out what port did Ratpack actually run on, and then stop it and ensure that it's cleaned up properly, because we don't want stray processes running after the tests. That's always a bad thing. We run in our tests with port 0 to automatically choose a random port, because otherwise, when you're running on random CI systems and developer servers, you can never depend on a fixed port being available all the time consistently. It just doesn't work well. In the functional spec, we start with the methods to actually run Gradle tasks. We have them either as build or build and fail. Those are capabilities provided by the test kit. And we have a bit of use of the Gradle test kit's Gradle runner builder to say, this is the project you're to use, which was set up in the test. We're going to pass some flags and options to it. And here's our arguments. We also have some utilities for creating files, which is not particularly interesting. But in our setup method, which is run before every test, we create a starting point for a build file. We need to use a local Maven repository, just some arbitrary directory within the project dir, because we want this project to run the tests against our currently built snapshot version of Ratpack plugins, not one that's published off into JCenter or some external repository. So we need some way to pull that in. We also need to make sure that we declare that we're using the right version, so we have that as a token as we're creating the file. This file is just a starting point. Many of the tests actually append onto it to add further declarations based on whatever it's trying to test. But this is a good starting point. It gets us the ability to actually resolve the plugins, the application of the plugin, and then other things can be added in the individual tests. Here's the method which we use to scrape the port. Effectively, we start a separate thread which watches the process to capture the output where it says Ratpack is now running on port blah, 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 parses it, and then we wait for that to actually happen, in which case we grab the result, or timeout, in which case we consider it a test failure. That's what we have for the basics of our plugin testing. We obviously have many other tests that are run as part of the Ratpack project, but they aren't plugin specific. They're just whatever logic it is we need for testing the main Ratpack web framework, the various modules that go along with it, etc. So let's look at the Ratpack project's build now. As I said, we have quite a few different modules. We've got maybe 4 or so sort of core-ish modules that are used for the Ratpack framework, plus the different modules that are commonly pulled in as part of our plugins. We've got the Ratpack plugins themselves, which are a module that are published separately. Then we've got, I'd say, maybe 10 or 20 modules related to integrations with various third-party frameworks, and a handful of modules that are used for internal purposes, such as generating the documentation, running the Ratpack public website, which is also a Ratpack app, doing internal testing, performance testing, etc. So with that many projects, it can be sort of tricky to keep track of them. And if you need to switch between projects quickly, it can be a real pain to find the right build file if they're all named build.gradle. What this snippet does when you put it in your settings.gradle is it allows you to change the naming for build.gradle to match the name of that subproject. So instead of build.gradle for every single module, we would have RatpackCore.gradle, RatpackJuice.gradle, RatpackGradle.gradle. And in an IDE or other editor, you can just say navigate to file and type the name of the module and quickly get to the build file for that module, as opposed to needing to scroll through a list of many, many files named build.gradle. Not a big thing, but it comes up more often than I care to remember. Similarly, as the project grew in size, we saw that we had more and more redundancy between different build files, as well as cases where particular shared build file sections were getting sort of large, and we wanted to factor an aspect out of that build file so that it could be in its own file and more comprehensible there than intermingled with a whole bunch of other stuff. So we have a Gradle directory within the root of our project, and within there we have various different build files which are imported into the build files for our individual modules. Some examples of functionality that we've extracted out of the build files individually and into these sort of shared build file snippets are reporting on different types of quality static analysis, our rules for how we manage dependencies, how we build standard Groovy and Java modules, as well as various details related to publishing. In the Ratpack plugin, we saw that we needed to know what version are we currently running. Likewise, Ratpack Core exposes the version as something that can be used by applications if they want to report on the framework versions that they're using, etc. In order to do both of those, we need somewhere where at build time or runtime, those modules can know what version to use. We could just hard-code it in a class or in a version resource and manage it manually, but that's not particularly elegant. And it's very likely that at some point someone will forget to update them. And then it'll be giving misinformation saying, hey, I'm version 1.0 when you're actually 1.1. That's no good. So we automated it. In here, we're declaring a new task, write version number file, and we say, OK, here's the path where it should be. Very importantly, we specify inputs and outputs. We specify an input property with the version from the Gradle project, and then an output for the version file that we're going to write out. If we hadn't done these, then the task would not work properly with incremental build support. That is, if you update the version of the project, it wouldn't treat that as something that actually requires rewriting this file. And until you did a clean build, it would still have the old file. Likewise, if you didn't declare the output, when it rewrites this file, it wouldn't update any of the other tasks that require it. So it wouldn't update the resources. Then we declare dependencies so that it knows the resources depend on this file. So does IDE generation, because we actually want this file generated before you run Ratpack, regardless of whether you're running it through Gradle or through a dumb IDE. Hopefully you're running an intelligent IDE, but whatever. Similar to that, we also have a resource where we track the minimum version of Groovy. This we don't pull from the project version because that would be nonsensical. We instead pull it from the dependencies that we've declared. We say we're going to use Groovy 157, that's just a random number, and then that same version is written out to this resource file. In this case, we didn't actually create a new task. We just added a new action at the beginning of the existing process resources task. The reason why the other version I used a new task is because we wanted to be able to declare dependencies on it. And you can't declare dependencies on individual actions. You can only declare them on tasks. But if you don't need any dependencies, this is a slimmer way to do it. In order to ensure a consistent build environment, it's really useful to automate as many checks as you can and detect if the environment is in an unsupported state and tell the user immediately, rather than waiting to be halfway through an hour-long build, hopefully not, and then have it fail with a nonsensical error message. So, when you have things that you need to check them up front in the build and give a clear error message. In this case, we need the file encoding for the JVM to be UTF-8. We also need at least Java 8 to be present for the build. If either of those isn't the case, we fail immediately. And we get a lot fewer support requests saying, hey, I tried to run this with Java 7 and it didn't work. Well, it isn't supported. It said it clearly right there. Sometimes it can be helpful to work offline, such as on an airplane traveling to a conference. In order to do so, Gradle has a -- offline option, which makes it so that any dependencies that it needs to run the build, it goes to the cache without trying to go over the network to load the new version. But if you don't have the needed artifact in your cache, it just won't run. It'll tell you, hey, I need this artifact, but it's not in your cache. So before you go offline, you somehow need to get all the artifacts into your cache. You could do this by running Gradle build, Gradle test, Gradle Jacoco, Gradle checkstyle, all of the different tasks you could possibly need to run. But you're almost certainly going to forget something, and the individual tasks may take some time to run. Running the build is a lot slower than just downloading the files. So this little task allows for just going through all of your configurations, regardless of what they're used for, and downloading them, all of them, and giving you a little bit of status feedback as it's going. It was really useful before preparing for this talk, because I knew I was going to need to do some Ratpack something, and one task, download it all, do everything else offline. As you get more and more modules, you're more and more likely to have dependencies that are shared in common between some of them. For example, we use SLF4J in almost every module of some sort in the Ratpack project. We also have a fair number of dependencies on Netty, Spock, and several others. You could just hard code the same version in each build file, but then you've got a maintenance nightmare. What we do here is we declare an extension property and say, OK, here are the common versions, and declare those versions exactly once in that shared location. And whenever we need to update them, we go to that shared location and change it one place. And all of the places that need to use that version, I declare commonversions.netty as part of their dependency declaration. And these versions can be used for things other than just dependency declarations. For example, some of them we automatically tokenize into our website or our manual in example build files in documentation, various uses for this information. Sometimes we don't just have a version that we have shared, we have a full dependency. That is also including the group ID, artifact ID. And in those cases, it's handy to have a common dependency set as well as the common version. And that allows for even more complicated and helpful things to be externalized, such as dependency exclusions. If, when we're pulling in a dependency on Spock, we don't want to use their version of Groovy all ever, we want to use our version of Groovy, we can declare that once in the common dependency, and then everywhere else can just get that configuration automatically. While it's not shown, that sort of syntax can also be used with a list of create dependencies to have a single common dependency declaration actually pull in multiple artifacts. Another thing that this is really useful, having common versions, is when you have multiple modules that are part of the same project and thus should really be on the same version. For example, when you have SLF4J bindings and you want to pull in the same version of the JCL, JUL, log4j backends, bridges, whatever, you can use that same version reference and not need to worry about them getting out of sync. Similarly, Netty, Jackson, all of those have tons of add-on modules that you really want to use the same version. The Groovy project has a CI server that they use for testing compatibility of new versions of Groovy with commonly used community projects. And in order to run with an alternate version of Groovy than the one that Ratpack normally builds with, we added support for specifying the version of Groovy as an environment variable. We can then use that environment variable to change that common version and have a single point that we integrate that update rather than needing to go to a set of 5, 10 projects and change their dependencies one by one. In this case, when it's changed, it's usually for some snapshot version, which isn't resolvable from our default repositories. And thus, we also declare an additional repository to download the snapshots from. There's a few other things that I don't really have time for, but I will talk about this. There's a whole bunch of tests and different projects in the Ratpack build, and if you run everything one at a time, it takes a long while to build. To help improve the performance, there's actually 3 different levels of parallelism built into the Ratpack Gradle build. The first is test parallelism. Running a test task, we have it configured so that it can actually fork out multiple test runners and run the tests in parallel with each other. That's just as simple as declaring test max parallel forks, in this case 3. That can have some impact when you're running on a cloud CI platform where you're limited as to how much memory you can use. So we had to do a whole bunch of tweaks to rein the memory usage down so that it fits within a 1 gig or so limit. That being said, we also disable that level of cloud parallelism when we're in Cloud CI, which we detect using environment variables. But on a development machine, it helps speed it up a lot when you can run the tests in parallel. When you've got thousands of tests, run 3 at a time, and you'll get done faster. In addition to that, there's 2 other levels of parallelism. There's cross-project parallelism, which is enabled via the -- parallel flag and the -- max workers. This is currently an incubating capability and may change a bit, but it seems to work pretty reliably. That doesn't allow tasks within a project to run simultaneously. It only allows projects that have no dependency on each other to run in parallel with each other. But when you've got 28 subprojects, once you get the core dependencies for them complete, you can run a few at a time and get some decent speed up. It does get a little confusing in the build output, though, seeing an output message from one project, then another, and then another interleaved. But so be it. It's worth it for faster build times. The third level is intra-project parallelism. This is where it actually runs tasks within a project in parallel with each other. That is also an incubating feature and relies on enabling it with an undocumented system property, which is right up there. That does not always work 100% flawlessly in my experience. Sometimes it results in sort of weird, non-reproducible build failures. So use that one at your own risk, but I expect it to come along in the future and be a very useful addition to performance tuning. And that's what I've got, and I'm already 6 minutes over. Questions?
So the generated version file.
Yep.
The reason that's going to the source main instead of into like the build source main container directory? It's usually not considered best practices to throw it back into your source code directory.
That's a good question. I'm not aware of why exactly he did it that way. Luke Daly is the one who added that portion.
Probably another plugin picking it up and putting it in the jar. That's what you see with Maven.
Might be.
You could have added that other directory that
Yep.
to the thing. So
I agree. That's the pattern I've generally used on other projects, having a build directory for generated resources and keeping it separate from the main resources. That is a viable alternative and one I generally recommend over this, actually. Yes?
You did something where you assign your Ratpack dependencies to code instead of, could you possibly use transitive dependencies there? Is there a reason?
Where are you talking about?
Exactly, but you were doing, there were like specific versions of Ratpack dependencies on one
Okay.
project.
Yeah, I got you. So that was here, I think,
Earlier.
with the dependencies.create.
it was the dependencies function. So you do dependencies.
Okay. Yeah, the function of that, which is back, not in the testing, in the extension. Here?
Yeah.
So the reason for that method is so that when people are depending on particular Ratpack modules, they don't need to worry about what version of Ratpack or what the group ID for Ratpack modules is. They just need to know which module from Ratpack they want to load. That is, we're taking care of specifying the group and version for them. This doesn't actually add it as a dependency by itself. It only creates the dependency object, which you'd then specify which scope to put it in. So you'd do compile ratpack.dependency rx. Or I compile test ratpack.dependency ratpack test. So the dependency declaration still goes in your build file, but this is a shorthand to get the right one. Anyone else? Seeing none, I'll be around for the rest of the conference. If you want to talk Ratpack, Gradle, whatever with me, feel free to step up. I'll say hi, and we can talk about whatever. Thanks, everyone.